Hello, BR549 here, and a while back on the forum there was some interest in being able to generate a single high voltage pulse along a sine wave, and so I had a little spare time and thought I'd work on that for a little bit, and I'll show you my results. This is the device here, and I have a circuit board and a CDI ignition system, interface, and coils. So I'd like to show the concept. Show the concept here first on paper, and it may have to be done in two videos. I may have to do this section first and then do the actual operation, scope shots, and so on a second video, depending on how much time it takes. So what I did, and there's a lot of different ways you could do this. I used a microprocessor, SX28, runs at 75 megahertz, and you could do it with a programmable divide by n counter and eliminate the processor if you're not into the computer stuff. So in a nutshell, I'm using 120 volts sine wave off the line, and I feed that into a polarity detector, and the polarity detector outputs a positive pulse as long as the sine wave is on the positive side of 0. And I also feed it into a zero crossing detector circuit, which gives me a negative going pulse each time that the sine wave crosses 0. So I feed those two pulses into my microprocessor, and also I use two other inputs for push buttons, advance and retard, and that changes the value of a counter internally, either increments it or decrements it, which allows for my high voltage pulse to be moved along my sine wave, different locations. And then the output of the embedded controller or processor goes to an optical interface. Actually, it's an optical interface with a FET that isolates my processor 5 volts from my CDI ignition module and flyback voltage, which is 14 volts. So the pulses my CDI ignition system, pulses a flyback, and gives me a high voltage output. Okay. So again, I have my sine wave feeds my polarity detector circuit, which gives me a high output as long as my sine wave is on the positive side of 0, and a negative output, or a ground, when it's on the negative side of 0. And a zero crossing detector, which gives me a pulse, negative going pulse, each time that my sine wave crosses 0. Those two pulses are fed into my 75 megahertz SX embedded controller, and I have, again, two push buttons. One's to increment my counter, one's to decrement the counter. that I'm using to determine at what time that along my sine wave the output pulse is generated. My interface, which I call SX controller to CDI interface, which is what it does, and it, in a nutshell, optically couples my processor to my CDI ignition system, and the output, when I pulse that, send it a pulse, the output pulses my flyback transformer, which in turn generates a high voltage pulse at a particular location on my sine wave. So, since this is a processor, it's program driven, and this is just a general program flow, pretty straightforward. I have a counter, I call counter A, and it's originally set in the software to a predetermined value, which generates when you start the processor. It just puts that pulse in a predetermined location for startup. I tried to get it fairly close to where I wanted to work, so I didn't have to move the pulse too far once I started the processor. And so once it's running, it looks for the zero crossing detector pulse, and if it's not low, then it loops back and it continues to watch for that pulse until the pulse goes low, indicating it's crossing zero, and drops through, and then it starts looking for the polarity detect to see if it's on the positive side of the sine wave. If not, it loops back through, and once both these conditions are satisfied, then it drops down to the counter stage, which it decrements the counter A, checks to see if the counter is zero. If it isn't, it loops until decrements, checks, until the counter is zero, and then it outputs a pulse to the CDI system, and then it checks to see if my push button, my increment push button is on. If it is, it increments the counter. If not, it checks to see if the decrement push button is pressed. If it is, it decrements the counter. If not, it loops back through and does the same process again. So normally I don't draw the entire circuit. I have a CAD system and I do the boards, but I did show the important parts of, I think, the important parts of this circuit, which is a zero crossing detector circuit and a polarity detector circuit, and I also have the SX, the interface circuit here. So I got this circuit off the internet. It works fine. So you can find them on the internet. All you do is search under zero crossing detector, and there's a lot of them out there. This one worked good for me, so that's what I used. And so I'm not going to go into a lot of detail other than the fact that it gives me an output pulse when my sine wave crosses zero. And this is the polarity detect circuit here, and this is just basically an optical coupler with a 60K 5-watt resistor in series with the input to the optical coupler, and when it's positive, when the sine wave is positive, then it turns the LED on, turns the transistor on, and when it's negative, it shuts it off. So this, I just noticed something here. The output actually is right here. This 5-volt in. This is my output right here. Okay. And again, this is the interface that goes between my processor and drives my CDI output to the CDI ignition system. And I used VO3120, which is an optical coupled FET driver. And again, I used what I had on hand. I could have used a FET, like a 4060 or something like that, or a 460, but I used an insulated gate transistor, which drives my CDI ignition system. Again, I didn't draw the whole circuit out. Normally when I do my circuits, it's all done in this format. I do it on a CAD, so it's just the way I do it. It makes it easier. But looking at the board, there's 0 crossing detectors here. My sine wave polarity detector circuit is here. Of course, this is my processor. This is my power supply filtering for my 5 volts. Originally I had a transformer on it. I removed the transformer and I just supplied 12 volts off of a battery to the board to generate the 5 volts to run the circuit board. Reason I did that is because I was getting some high voltage noise back even with all the filtering, and it was causing problems with my processor. Okay. So I'm going to stop here on this video because I'm running out of time, and then the second video I'll show operation and waveforms of where I'm at on the device right now. Thank you.